Good morning everyone and welcome to the lecture series on Laplace transforms. In this lecture, we shall study about the Laplace transform solution of initial value problems, which consists Laplace transform of derivatives and Laplace transform of integrals. So let us recall what is the Laplace transform of a function. Let ft be a function defined for t greater than or equals to 0. Then the integral of this form, integration from 0 to infinity, e raised power minus st ft dt, is called the Laplace transform of the function smaller t, which is represented by capital F, which is the function of s, where s is the Laplace transform parameter, and e raised power minus st is the kernel of the Laplace transform, and provided this integral is exist, and inverse Laplace transform of this function capital F is equals to the actual function, which is small f over t. So let us first we define Laplace transform of derivatives. So in this section, we define the Laplace transform of the derivatives of the function if we know the Laplace transform of the actual function. So Laplace transform is the one of the important tools of solving the initial value problems. So first we prove the following results on which the method of solution depends. Let ft for t greater than or equals to 0 be a continuous function and be of exponential order on the interval 0 to infinity. And let f prime t, which is the first derivative of the function ft, be also exponential order and at least piecewise continuous over the interval 0 to infinity. And if Laplace transform of actual function f equals to capital F function of s, it means if Laplace transform of actual function is exist, then we can find the Laplace transform of the derivative of the function f, and which is given by this relation. So Laplace transform of first derivative of the function f is equals to s times Laplace transform of the function f minus function's value at 0. So we have to exclude the proof of this theorem. For the detailed proof, you may go through the notes which I have already provided you. So this is very important result when we know the Laplace transform of the function and we are interested to find the Laplace transform of the derivative of the function. So Laplace transform of the first derivative of the function is s times Laplace transform of f minus function value at 0. Here s is the Laplace transform parameter. So to apply this result, we need to remember this result. So especially if value of this function at 0 equals to 0, then Laplace transform of the first derivative of the function f equals to s times Laplace transform of f, or you can also write inverse Laplace transform of s times s f of s equals to f prime t. It means inverse Laplace transform of this equals to actual function of the, which is first derivative of the function, or you could also write this d upon dt equals to into L inverse Laplace transform of s. It means this result is very useful when your Laplace transform is can be written in this form, s times Laplace transform of small f, right? So this result is useful in finding the inverse Laplace transform when given function phi s can be written as s times f of s, right? So let us see generalization of this theorem. It means previous theorem for the Laplace transform of the first order derivative. In this theorem, we define the Laplace transform of the nth derivative of the function. So let f prime t nth derivative, n minus 1th derivative of the function t be continuous function over the interval 0 to infinity and be of exponential order, and let the nth derivative of the function be at least piecewise continuous on the interval 0 to infinity, and if the Laplace transform of the actual function f equals to capital Fs, it means Laplace transform of the actual function is exist, which is capital F, and its n minus 1 derivatives are continuous and of exponential order. then the Laplace transform of the nth derivative of the function is given by this relation, s ki power n multiplied by Laplace transform of f minus s ki power n minus 1, function value at 0 minus s ki power n minus 2, first derivative of the function at 0 and up to n minus 1th derivative of the function at 0. So this result is very important to find the Laplace transform of the derivatives of the function, first derivative, second derivative, and so on. So it means previous theorem is the special case of this result 3. It means if we put n equals to 1 in this relation, then we find the Laplace transform of the first derivative of the function. So s times f of s minus f of 0. Special case, if the function values and its derivative values at 0 equals to 0, then Laplace transform of this nth derivative equals to s ki power n times Laplace transform of s f, right? So this is the Laplace transform of the nth derivative of the function when the values of the function and its derivative at the initial point 0 is 0. Then nth derivative is given by Laplace transform of nth derivative is given by this relation, or inverse Laplace transform of this term is given by the nth derivative of the function, which can be written as nth derivative of the inverse Laplace transform of capital Fs, right? So these two results are very important to find the Laplace transform of derivatives. So let us see application of these two theorems. Find the Laplace transform of sine square t using the differentiation formulas given in above theorem. So let us consider that this function ft equals to sine square t. We do not know the Laplace transform of this function, but if we differentiate this function one time, then we get first derivative equals to sine 2t, and we know the Laplace transform of sine of 2t, which is 2 upon s square plus 4, and value of this function at initial point 0 is 0. So if we apply the previous theorem 1, Laplace transform of first derivative, so now the basic property of the Laplace transform of derivative, it means Laplace transform of first derivative equals to s times Laplace transform of small function f minus function value at 0. So it means Laplace transform of sine of 2t. It means first derivative of the function is sine of 2t, and this is s times f of s minus 0 because function value at 0 is 0. So this is s times of fs, and we are interested to find the inverse Laplace transform, basically Laplace transform of this actual function sine square t. So it means this capital F is the Laplace transform of small f. So from here, Laplace transform of sine of 2t equals to 2 upon s square plus 4, which can be evaluated by using previous lecture. So this is equals to s of fs. Now using the elementary formula, and if we simplify this, then we get capital Fs equals to 2 upon s times s square plus 4, which is the Laplace transform of the function ft equals to sine square t. It means these two formulas, it means Laplace transform of first derivative or Laplace transform of nth derivatives, are very useful to find the Laplace transform of the functions whose derivatives exist. All right. Let us see. Now we are now in a position to outline the procedure for solving the initial value problem. As we know, the initial value problem consists derivatives of the function. So consider the initial value problem: a times y double prime plus b times y prime plus cy equals to function of t. Here prime denotes the first derivative and double prime denotes the second derivative of the function y with respect to the independent variable t. As this is our second order differential equation, so we need two conditions at the initial points. So there are two conditions given. Value of the function at 0 is suppose y naught, and value of the first derivative of the function at 0 is y naught prime, where a, b, and c are the constants. So to solve such type of initial value problems, we take the Laplace transform of the both side of this differential equation. and denote the Laplace transform of the dependent variable y equals to capital Y, which is the function of s, and Laplace transform of this right hand side, which is function of t, equals to capital S, and use the previous theorem. It means Laplace transform of the derivatives theorem. So we obtain here, this is Laplace trans. If you take the Laplace transform of this term, it means Laplace transform of second derivative. So put n equals to 2 in the Laplace transform of the derivative theorem. So this is a times s square capital Y minus s multiply y at 0 minus y prime at 0 plus Laplace transform of the second term. It means Laplace transform of first derivative. So this is b times s capital Y minus y0 plus Laplace transform of this third term c times capital Y equals to Laplace transform of right hand side. Now, if we simplify this relation by using these two initial conditions for capital Y, then we get this one. Capital Y equals to Fs plus A times S multiplied by Y at 0, Y prime at 0 plus B times Y at 0. As square plus Bs plus C. It means this is our Laplace transform of the dependent variable y, which is given by this relation. Now, if we take the inverse Laplace transform of this relation, then we get the solution of the initial value problems in terms of small yt. So yt equals to L inverse of capital Y equals to L inverse of this one. Right? So to solve the initial value problem, first we take the Laplace transform of the given differential equation and simplify for the Laplace transform of the dependent variable y. Right? And then we take the inverse Laplace transform of, then we get the required result in terms of the dependent variable y. So let us see application of Laplace transform to solve the initial value problem. So solve this initial value problem, y double prime plus 4y equals to 0, where initial condition at 0 is 1 and its derivative is also 6. So to solve such type of problems, first we take the Laplace transform of the given differential equation, and let represent the Laplace transform of this dependent variable y equals to capital Y. So Laplace transform of this first term, it means Laplace transform of second derivatives. It means put n equals to 2 in the Laplace transform of nth derivative relation. So this is s square capital Y minus s times y at 0 minus y prime at 0 plus 4 times of Laplace transform of y, which is capital Y, and right hand side is 0. Now, if we substitute the value of the function and its derivative at 0 in this relation, then we get s square plus 4 times capital Y equals to s plus 6. Now, if we simplify this relation for capital Y, then we get s plus 6 upon s square plus 4. If we simplify again this, then we get s upon s square plus 4 and plus 6 upon s square plus 4. Now, to find the value of small y, we need to take the inverse Laplace transform of this term, and we know that inverse Laplace transform of this first term is cos of 2t, because this is the Laplace transform of cos of 2t, and this is the Laplace transform of sine of 2t with some constant multiplication. So now take the inverse Laplace transform of this relation, then we get y is the function of t, which is equals to inverse Laplace transform of capital Y equals to L inverse of each terms here. So we use the linear property of the Laplace transform. So inverse Laplace transform of this first term is cos of 2t, plus here if we take 6 common out, then we know that the Laplace transform of sine of 2t equals to 2 times 1 upon s square plus 4. And if we simplify, then we get 3 times sine of 2t. Like, so it means for the initial solution of the initial value problem, first we take the Laplace transform of given differential equation and use the conditions of the problem and simplify for the Laplace transform of the dependent variable, and then we take the inverse Laplace transform of the dependent variable, then we get the solution in terms of the dependent variable. Right? Let us see one more example based on solution method of initial value problem. To solve the initial value problem, y double prime minus 5 times of y prime plus 4y equals to e raised power 2t with condition at 0 equals to 19 upon 12 and first derivative at 0 equals 8 upon 3. So take the Laplace transform of the given differential equation with the assumption that Laplace transform of this small y is capital Y. So and use the Laplace transform of nth derivative relation. So Laplace transform of this first term, this is s square times capital Y minus s times y at 0 minus y prime at 0 minus Laplace transform of the second term, which is s times capital Y minus y0 plus Laplace transform of this third term, which is 4 times capital Y equals to Laplace transform of right hand side. This is exponential function, and we know that Laplace transform of e की power 2t equals to 1 upon s minus 2. Now use the given conditions y at 0 and y prime at 0 in this relation, then we get s square minus 5s plus 4 times capital Y equals to 1 upon s minus 2 plus this term, and if we simplify then we get 1 upon s minus 2 plus 19 s minus 63 upon 12. Now if we simplify this relation for the capital Y, then we get capital Y equals to 1 upon s minus 2, s minus 1 and s minus 4, because linear factor of this relation, quadratic relation, is s minus 1 times s minus 4 plus 19s minus 63 upon 12 times of s minus 1, s minus 4. Now here each term is linear factor, right? So by using partial fraction method, we can separate these terms. So there are three terms, s minus 1, s minus 2 and s minus 4. So by using partial fraction method, we separate these linear factors. So we get minus 1 upon 2 times of s minus 2 plus 14 upon 9 times of s minus 1 plus 19 upon 36 times s minus 4. And now to solve the to get the solution, we need to take the inverse Laplace transform of this relation, and the inverse Laplace transform is given by yt equals to minus 1 upon 2 times as, and we know that 1 upon s minus 2 is the Laplace transform of e raised power 2t, and 1 upon s minus 1 is the Laplace transform of e की power t, and 1 upon s minus 4 is the Laplace transform of e की power 4t. So Laplace solution of this problem is given by this relation. So to find the solution of the initial value problems, we need to know the Laplace transform of the elementary functions. Elementary functions means constant function, exponential function, polynomial function, and trigonometric function and hyperbolic functions, because we use directly them. Right? Now, Laplace transform of integrals. In the previous section, we studied about Laplace transform of derivatives. So in this section, we shall study about Laplace transform of integrals. So in many problems of electrical engineering, it means LC circuit or RC circuit problems, we encounter integral differential equation. Integral differential equation means the relation which consists derivatives as well as integrals. So such type of relations known as integral differential equations. If Laplace transform method is applied to, we need the formulas for the Laplace transform of an integral. Such a formula is represented in the following theorem. For the detailed proof, you may go through the notes which I have already provided you. So let small f for t greater than g equals to 0 be a piecewise continuous function and be of exponential order on the interval 0 to infinity. Then Laplace transform of the integral of the function and integration limits from 0 to t equals to Laplace transform divided by s. So if you remember the Laplace transform of the first derivative, which is s times capital multiplied by capital F. And integration part, Laplace transform of integral is Laplace transform divided by small s. It means if your Laplace transform is multiplied by s, then we use Laplace transform of derivative formula. And if your Laplace transform is given by f divided by s, then we use Laplace transform of integral formula to find the inverse Laplace transform of given Laplace transform. So it means inverse Laplace transform of capital F divided by s equals to integration from 0 to t f of tau d of tau. So keep here mind, if your Laplace transform is given multiply by simple s or and Laplace transform of small f, it means s into fs form, then we use Laplace transform derivative formula. And if your Laplace transform is given by f upon s, where capital F is the Laplace transform of small f, then we use Laplace transform of integral formula. Clear? So let us see application of this formula. To solve the initial value problem, y prime plus 3y plus 2 times integration from 0 to t y of tau d of tau equals to t, and where initial value is 0. So to solve this problem, we take the Laplace transform of given integral differential equation, because here derivatives as well as integral exist. So we get, so Laplace transform of this first derivative term is s times capital Y minus y at 0 plus Laplace transform of the second term, which is 3 times capital Y, plus Laplace transform of this integral term, and which is Laplace transform of this integrand divided by Laplace transform parameter. So this is 2 upon s times capital Y equals to Laplace transform of this polynomial of degree 1, which is 1 upon s square. Alright, now if we simplify this relation by using initial condition, then we get s square plus 2 plus 3s times capital Y equals to 1 upon s. And if we simplify this relation for capital Y, then we get 1 upon s plus 1 plus s plus 2. And this can be written as 1 upon s times of capital S, f, right? It means this Laplace transform can be written as 1 upon s times capital Fs, because here divide by this relation is divided by small s. And if your Laplace transform of this form, then we can use this relation. It means if your Laplace transform of this one, so to find the inverse Laplace transform, we use this relation, this one. Like, so here capital Fs is 1 upon s plus 2, s plus 1. Now by using partial fractions, we get these two linear factors, 1 upon s plus 1 minus 1 upon s plus 2. And we know the inverse Laplace transform of this relation, because 1 upon s plus 1 is the Laplace of e ki power minus t, and this is 1 upon s plus 2 is the Laplace of e ki power minus 2t. So inverse Laplace transform of this term would be ft equals to e ki power minus t minus e ki power minus 2t. So therefore the inverse Laplace transform of this one, this relation is given by integration from 0 to t f of tau d of tau, and f of t is given by this relation. So this is integration from 0 to t e ki power minus tau minus e ki power 2 tau, and integration with respect to tau. And if we simplify this integral term, then we get 1 upon 2 times of e ki power minus 2t minus e ki power minus t plus 1 upon 2. So this is very important again. If your differential equation consists integrals, then we use Laplace transform of integral formula. So let us see one more example based on application of Laplace transform of integral. So find the inverse Laplace transform of 1 upon s times s square plus 9. If we remember, if your Laplace transform is given by divide by s factor, then we use Laplace transform of integral formula. So here, if we consider capital Fs equals to 1 upon s square plus 9, then its inverse Laplace transform, as we know that this is constant times 1 upon s square plus 9. So its inverse Laplace transform would be 1 upon 3 times sine of 3t, because this is the Laplace transform of sine function. So inverse Laplace transform of this is 1 upon 3 times sine of 3t. So inverse Laplace transform of the actual Laplace function, which is given by 1 upon 3 times of integration from 0 to t sine of 3 tau d tau. Now if we simplify this integral relation, then we get 1 upon 9 times 1 minus cos of 3t. So thank you for today, and in the next lecture we shall study about the Laplace transform of higher derivatives terms, or Laplace transform application of Laplace transform by using